A database index is a data structure designed to enhance the efficiency of queries and data operations. With indexing, the database can quickly locate target data without having to scan the entire table. Different types of indexes are suitable for different application scenarios, each with its own strengths and limitations. The B tree, or its variant B plus tree, is the most common index type in relational databases, primarily used for sorting and range query operations. Working principle. A B tree is a balanced tree structure where nodes contain pointers to other nodes or rows of data. With a B tree index, the database can locate specific data with a time complexity of O log n. The B plus tree, a variant of the B tree, stores all data in its leaf nodes, which are linked in order, facilitating range queries. Advantages. Supports range queries. B plus tree nodes are arranged in sequence, making it suitable for range queries. Ordering. Data is stored in an ordered manner, supporting sorting operations. Widely used, almost all mainstream databases support B tree indexes. Disadvantages. Decreased insert/delete performance. When data changes frequently, B tree indexes need to frequently adjust the tree's balance, leading to performance degradation. High space occupation. The tree structure is complex and may require more storage space for larger datasets. A hash index is based on a hash function that maps key values to fixed-sized buckets, making it ideal for equality searches. Working principle. The index key is converted into a hash value using a hash function, which is stored in the corresponding hash table location. When querying, the hash function directly computes the hash value, enabling data location in O(1) time complexity. Advantages. Fast query speed. Excellent performance for equality queries, with lookup time complexity of O(1). Efficient key value mapping. Ideal for scenarios requiring frequent exact value lookups. Disadvantages. Does not support range queries. Hash indexing cannot handle range queries, as the hash function disrupts the data order. Hash collisions. When multiple keys map to the same hash value, hash collisions occur, leading to performance degradation. Space waste. Hash tables may be sparse, leading to potential storage space waste. A full text index is designed specifically for text data, enabling quick searches for words within text. Working principle. A full text index uses an inverted index structure to store each word found in documents and creates a mapping between words and the documents they appear in, significantly accelerating text search. Advantages. Ideal for large text queries, highly efficient for searching massive text data, and supports complex text matching. Supports keyword searches, allows for queries like match, enabling fuzzy searches and keyword matching. Disadvantages. Complex index maintenance. Frequent updates to text data require constant index maintenance, which may impact performance. Large space usage. Storing inverted indexes requires substantial disk space. A bitmap index uses bitmaps to store different values in a column and is generally suited for low cardinality columns, columns with a limited range of values, like gender or status. Working principle. The bitmap index creates a separate bitmap for each unique value, with each bit in the bitmap corresponding to a row of data. When a query is made, bitwise operations can quickly determine the rows that meet the criteria. Advantages. High query efficiency, optimized for multi-column composite queries, especially those involving Boolean operations. Efficient space utilization, very space efficient for low cardinality columns. Disadvantages. Low efficiency for inserts and updates. Bitmap indexes are better suited for static or infrequently changing data, as any data change requires recalculating the bitmaps, which is resource intensive. Not suitable for high cardinality columns. When a column has many unique values, the bitmap index becomes inefficient. Different types of indexes serve various roles in database applications. B-tree indexes are suitable for most queries, hash indexes excel in equality lookups, full-text indexes are designed for text searches, and bitmap indexes are ideal for analytical systems. Thanks for watching. For more information, please visit bauzier.com. A Bloom filter is a highly space-efficient probabilistic data structure used to determine whether an element belongs to a set. Its key feature is that it allows for a certain false positive rate, i.e., it may incorrectly indicate an element is in the set, but it ensures that no actual elements are missed. Bloom filters are well suited for scenarios requiring quick verification of element existence within large datasets, especially when space is limited. How Bloom filter works. A Bloom filter uses a fixed-length bit array and multiple hash functions to store information about the set. The specific steps are as follows. 1. Initialize the bit array. The core of a Bloom filter is a bit array of length m, all bits initially set to 0, which stores information about elements in the set. 2. Adding an element. To add an element to the Bloom filter, the system uses k-hash functions to hash the element, resulting in k-index positions. The corresponding positions in the bit array are then set to 1. For example, if we add the element, apple, to the Bloom filter and have 3 hash functions that produce indices 5, 10, and 20, then these 3 positions in the bit array will be set to 1. 3. Querying an element. To check if an element exists, the Bloom filter applies the same k-hash functions to the element, generating k-index positions. If all these positions in the bit array are set to 1, the element is likely present. If any of these positions are 0, the element is definitely not present. Assume we have an empty Bloom filter and a 10-bit array. Initial state, all zeros. Adding the first element, apple, with hash function results of positions 2, 5, and 8. Adding the second element, banana, with hash function results of positions 1, 3, and 8. Querying for orange, suppose the hash function results are positions 2, 5, and 7. When we check the bit array, we find position 7 is 0, so we can confirm that orange is definitely not in the set. Querying for grape, suppose the hash results are positions 1, 5, and 8. Since these positions are all 1, the Bloom filter will return possibly present. However, grape was not actually inserted, illustrating the Bloom filter's false positive potential. Advantages are: 1. High space efficiency. Bloom filters use much less space compared to traditional hash tables or lists. 2. Fast insertions and queries. Since Bloom filters only require a series of hash computations, operations are very fast. 3. No false negatives. If a Bloom filter indicates that an element is not in the set, this is guaranteed to be correct. Disadvantages are: 1. False positive rate. Bloom filters may incorrectly indicate that an element is present when it is not, with the rate depending on the bit array size and number of hash functions. 2. Inability to delete elements. Once an element is added, it cannot be removed, as multiple elements may share the same bits, leading to incorrect deletions. 3. Increasing false positives with more insertions. As more elements are inserted, the likelihood of setting more bits to 1 increases, which in turn raises the false positive rate. Application scenarios. 1. Cache systems. Bloom filters are often used to check if a request is already in the cache. If the Bloom filter indicates that an element is not present in the cache, the system will directly retrieve it from the database. 2. Spam filtering, used to quickly determine if an email has already been marked as spam. 3. Duplicate detection. In large-scale data processing, Bloom filters can quickly check if an element has already been processed, thus avoiding redundant computation. Thanks for watching. For more information, please visit bauzier.com.
Spatial indices are data structures that optimize the querying and retrieval of spatial data, essential for applications where location or geometry is key. These indices are widely used in GIS, location-based services, computer graphics, and gaming, enabling fast spatial queries, proximity detection, and efficient storage and retrieval of large spatial datasets. An R-tree is a tree-based spatial data structure designed to organize multidimensional spatial objects. Each node contains multiple child nodes, and each child node is associated with a bounding box, representing the outer boundary of the spatial objects contained within that child. Leaf nodes store actual spatial objects, while non-leaf nodes contain pointers to child nodes and their corresponding bounding boxes. When inserting data, calculate its bounding box, locate an appropriate leaf node, and insert it. If a leaf node is full, it splits and the parent node's bounding box is updated. During a query, use the hierarchical structure and bounding boxes to exclude irrelevant nodes, thereby narrowing down the search area. Characteristics of an R tree include: 1. It supports dynamic insertions, deletions, and updates. 2. It minimizes search space through overlapping bounding boxes suitable for range and nearest neighbor queries. 3. It maintains relative balance during insertions and deletions, avoiding extreme depths and ensuring stable query performance. Pros are good query performance, adaptable to multidimensional spatial data, and supports flexible dynamic operations. Cons are overlapping bounding boxes may reduce query efficiency, especially in dense distributions. A KD tree is a binary tree where each node represents a point in k-dimensional space. Tree construction involves selecting a dimension to split data into two parts, typically by the median value. Different dimensions are chosen in rotation for splitting, creating a hierarchical structure. During insertion, data is split based on the selected dimension and median, allocating data to either the left or right subtree. For querying, the tree structure is traversed by splitting at each node's dimension, with potential searches in the opposite subtree if necessary. Characteristics are: 1. Suited for low-dimensional space data, performance decreases significantly with high-dimensional data. 2. Supports efficient nearest neighbor searches and range queries. Pros: simple to implement, effective for smaller, low-dimensional datasets, and provides high query efficiency. Cons: suffers from the curse of dimensionality in higher dimensions, leading to substantial performance loss. GeoHash converts geographic coordinates, latitude and longitude, into a one-dimensional string, using a grid-based approach to represent location. The length of the string determines spatial precision. The encoding result generates a GeoHash string, where shared prefixes represent spatially close regions. For queries, GeoHash prefix matching enables quick location of relevant data. It's ideal for quick storage and retrieval of geographic data, allowing for efficient range queries. Adjacent GeoHash strings correspond to spatially close areas, enabling rapid nearby area searches. Advantages: simple to implement, easy to compute, and allows fast retrieval and aggregation of geographic data. Disadvantages: limited precision for complex spatial shapes, and query performance is affected by string length. The Hilbert curve is a space-filling curve that connects points in a two-dimensional space recursively, allowing a one-dimensional line to cover every point in a 2D plane. It is generated by subdividing and bending in a way that retains spatial proximity. It is generated recursively, with the first level forming a small square and subsequent levels replicating the structure within each square. It maps points in 2D space onto positions on a 1D curve, following a predefined traversal order. For queries, spatial data is accessed based on the curve's mapped sequence. Advantages are: maintain strong locality in high-dimensional spaces, suited for range queries and clustering analysis. Disadvantages are: complex to implement, requiring curve generation and inverse transformation processing. Note that this is the most complex method, and we can have a dedicated session if there's enough interest. Thanks for watching. For more information, please visit bowsier.com.
Lambda architecture is a data processing framework designed to achieve high scalability, low latency, and high fault tolerance for large-scale data systems. By balancing traditional batch and stream processing, it leverages three layers: batch layer, speed layer, and serving layer. These layers work in tandem to provide efficient data storage, quick computation, and real-time data access. The batch layer's main objective is to generate a globally consistent data view, known as the source of truth. It stores and processes the complete historical dataset, conducting comprehensive calculations periodically to ensure accuracy and consistency. This layer is optimized for low-frequency, high-latency processing needs. Data storage. The batch layer typically relies on distributed file systems, such as HDFS or Amazon S3, for storing raw data. These systems ensure data reliability, persistence, and scalability, which are essential for maintaining large-scale historical datasets. Batch processing. Using big data processing engines like Apache Spark or MapReduce, the batch layer conducts periodic computations on the stored data. These can involve aggregation, statistics, or machine learning tasks, all aimed at creating accurate views, batch views, of the historical data. Batch view generation. After batch processing, the system generates a batch view containing results based on all historical data. These views are typically stored in distributed databases like HBase or Cassandra, and they offer high accuracy and provide a comprehensive data perspective. The batch layer provides a highly accurate data view, ideal for queries that require data consistency across the entire dataset. Batch processing takes significant time, leading to high latency. The speed layer is primarily responsible for handling the latest, incoming data to ensure real-time responsiveness. Unlike the batch layer, which processes entire datasets, the speed layer processes only incremental data. Although it lacks global consistency, the speed layer provides low-latency responses to recent changes, allowing the system to access up-to-date data. Real-time data ingestion. Once data enters the system, it immediately flows into the speed layer. This layer typically relies on stream processing frameworks like Apache Flink, Apache Storm, or Spark Streaming to capture and process data in real time. Incremental computation. The speed layer performs incremental computations on the incoming data. Unlike the full computations in the batch layer, only new data is calculated in the speed layer, generating the speed view. The results of incremental computations are stored in a speed view, usually using low-latency storage systems like Redis or Elasticsearch to support quick querying. The speed layer's incremental computations provide low-latency access to data, making it ideal for scenarios requiring rapid updates. Lacking a global data perspective, the speed layer's results may contain inaccuracies. The serving layer's main task is to integrate data from both the batch layer and speed layer, providing a unified query interface for users. Through this combined querying, users can access both the globally consistent data from the batch layer and the real-time data from the speed layer via a single interface, achieving both data accuracy and timeliness. Data storage. The serving layer uses high-performance databases such as HBase or Cassandra to store and manage both batch and speed views, ensuring swift responses to user queries. Query processing. When a user initiates a query, the serving layer retrieves data from both the batch and speed views and merges the results. The batch view provides globally consistent historical data, while the speed view supplies the latest incremental data, ensuring the query result reflects the most current data. Result merging. The serving layer merges data from the batch and speed views to provide a final query result. Typically, a query engine performs this, prioritizing the batch view and layering the speed view's incremental data on top to produce a near real-time output. The Lambda architecture achieves high scalability, low latency, and fault tolerance in large-scale data systems by integrating the batch layer, speed layer, and serving layer. The batch layer ensures data accuracy, the speed layer provides real-time updates, and the serving layer merges historical and incremental data, enabling high accuracy, responsive real-time queries. Thanks for watching. For more information, please visit bauzier.com.